So for this question, we're asked to look at the transfer function below and determine the settling time, peak time, and overshoot by assuming second order dominance, and then we're asked to justify whether the assumption is valid. So looking at our transfer function, we can see that it's already in the characteristic form. That means that we have a 1 in front as the constant for our highest power of s. So what I'm going to do is take out our characteristic equation and equate it to the general form. So the general form that we're going to use is s plus p sine of s squared plus 2 omega n zeta s plus omega n squared. So we're using this one because we're assuming that the second order part is dominant. So this is the second order part. Okay, we're going to assume that this is the bit that controls what the system actually looks like. The bit that is in here has almost no effect under our assumption. So we need to go through and work out p, omega n, and zeta. These two are the ones that are going to really control the system's response, so long as we have this dominance assumption being valid. So in order to do this, we need to expand out the brackets in here. Now I'm just going to write us out the nicely expanded version where all of the powers of s have been factorized. So we get an s cubed, an s squared, an s, and a constant on the end. So what we can do is go through and equate the constants in front of each s power. So we've got 1 in front of this one is equal to 1 in front of here. So the 24.2 has to equal what's in here. Okay. Next we have that 109, the s part, has to equal this s part. We then have that the constant on the end has to equal this constant on the end. So we end up with 3 equations with 3 unknowns. However, it's kind of a bit of a pain to try and go through and solve this manually. So I'm going to shortcut it a little bit and use this equation solver to do part of it. But basically, I'm going to rearrange this equation to get omega n zeta equals. And that means that the p goes to the other side, and I need to divide by 2. On this bottom equation, I'm going to do some rearranging as well. I want to get omega n squared on its own. And what I should then be able to do is I'm going to substitute omega n zeta into here, and that's just going to leave me with a p. And I'm going to put omega n squared as being equal to this. And again, it's going to replace it with a p. So the only unknown that's going to end up in the equation is p. So let's do that. Oops, sorry. I want to do it on the middle equation. So 109. So this gets replaced with this. This gets replaced with this. And there's a p on the end. So p is the only unknown in that equation. These are going to cancel out as well. So if you go through and apply a equation solver to this, just write out what I would type in. This. So we end up with 3 answers for p. So it can either be equal to 20 or 2.1 plus or minus 4.54i. Now, if we go back and look at the original form of our characteristic equation, we're looking for basically a p in here which is going to be part of the real axis, or sit on the real axis. This part in here is going to be where the complex conjugates can potentially come in. So a bit of a trick, I guess, just because it's annoying to solve the third order equation. So what I want to do is take the real answer, essentially. So I'm going to say p is this, not any of these. So once I've got that, I should be able to go back and figure out omega n and zeta. So applying this equation here and this equation here. So omega comes out to be 5 radians per second. And now you can use either of these to figure it out. So it comes out to 0.42 for the damping ratio. So what this tells us is, under the assumption that we have second order dominance, it means that we have an underdamped system. So therefore, when we go through and calculate now our time response properties, so it's asking for the settling time, the peak time, and the overshoot, we should be able to use the equations for second order underdamped systems. We'll come back in a moment and check whether the assumption is valid. So let's start with the settling time. So the equation for an underdamped second order system is, it's an approximate equation, so let me put in the approximate signs. 4 on omega n zeta, so we can pop that in. And it comes out to about 1.9 seconds. If we then look at the percent overshoot, and I dropped the times 100 to make it a percent. So filling it in, we end up with an answer of, again I dropped it, 23.4% approximately. And the other one that we were asked was that peak time. And this one comes out to 0.692 seconds. Alright, so that concludes actually finding these time response properties, but these are only under assumption of second order dominance. So now what we want to do is check the validity of the assumption. So how we do that is we need to figure out where each of the poles are in our system, and depending on the distance they are from the imaginary axis, we may be able to essentially cancel a couple out, cancel one out. So let's draw our imaginary and real axes. So before, we already found the pole, P equals 20. All right, so all we've got to do is figure out what values are going to cause our system to go to 0 for the bottom line. Okay, so this is our transfer function. Anytime this bottom line goes to 0, we've found a pole. So one of those is going to occur when S plus P goes to 0. So it's going to be when S is equal to negative P. And we said before that P was equal to 20. So this is one pole in our system. We can get another 2 from looking at what happens inside this quadratic formula. So I'll do it up here. All right. Now we can substitute in some values that we've worked out. So 2 times omega n, which we worked out to be 5, times 0.42 for the damping ratio. This works out to be 4.2s, and omega n was 5, so 5 squared is 25. So if you apply the quadratic formula onto this, so the negative b plus or minus square root of b squared minus 4ac divided by 2a, you end up with 2 answers. And they are that S is equal to negative 2.1 plus or minus 4.54i. Okay, so there are your two answers, and you'll notice that these are what also fell out before when we had to solve our equation down here. It was just that that wasn't the ones that we wanted for this part of the equation. So these are the locations of our poles. Let me just copy them down the bottom here. So let's mark them on our diagram now. So -20 is going to be somewhere out here. And we're going to have two poles, they're the complex conjugates. Maybe something like this. So this is -2.1 for the real part, and the imaginary parts are 4.54 and -4.54. So for dominance, what we need is this pole to be more than 5 times away from the imaginary axis than either of the others. So I'm going to write this as P divided by omega n zeta, which is the 2.1, has to be greater than 5. So subbing in, P is this 20, omega n zeta was this 2.1, and if you actually compute the number, it comes out to be 9.52. So this is true, this actually is bigger than 5, so therefore assumption is valid. Alright, so if we want to, we can actually verify it by looking at the MATLAB output. This is a code I've just quickly written to have that comparison. So this is telling MATLAB I want a transfer function. And G3 is the third order version of my transfer function. G2 is the one assuming second order dominance. And for that, I've eliminated the first order part. Okay, so we've only got the second order part here. So then I've decided to plot the step response of both of those, and this is what MATLAB has given me. So you can see that the response is pretty similar. So G3 is what happens when we have everything included. G2 is what's going to happen when we have second order dominance, and we've actually gone to the effort of eliminating the first order part. So it's very, very similar in terms of the response. Go and double check the values for each of the time response properties we're asked to find. If we look at the settling time, we can see that they're very close to each other for each of the different systems. Oops. So I managed to get them both up. So this one has a settling time of 1.73. G3 is the third order with everything in it. This one got 1.68, so that's pretty close. So definitely the second order part is dominant. And if we have a look back at what we got before when we did this manually, we estimated the settling time at 1.9, which again is pretty close considering this is an approximation formula. So if we have a look at the overshoot next, that's going to come from looking at the peak response on the graph. Let's flick them over. So we can see that we got overshoot of 23.3 and 22.6, again very close, so definitely the second order dominance thing is a good assumption. And if we look at what we got manually, we got a 23.4, okay. Next one is the peak time, and again we can get that off the graph. So the peak time, here we go, at time, so it's 0.702, this one's 0.746. If we have a look, we got 0.692, again it's pretty close to what we were expecting. So that's all there is for this question, and I'll see you in another video.